Black holes are the most bizarre and wondrous objects in our universe. They are entirely invisible yet beyond imagining. These are the regions where space, time, and reality are stranger than fiction. They're bottomless pits that devour stars, power the centers of galaxies, and warp space and time. If you get too close, the entirety of time may pass you by, and there is no return. However, for all we know about black holes, the big ones remain a mystery, particularly when they began forming. When the universe was still a baby, less than 1 billion years old, some of its stars turned into monster black holes. They grew to 1 billion times the mass of the Sun just 1 billion years after the Big Bang. But how did the supermassive black holes grow so fast? Well, the question has long plagued astronomers for decades, but now, thanks to a breathtaking discovery made by the James Webb Space Telescope, JWST, we might be closer to finding some of the answers. The world's most powerful telescope, the JWST, has just discovered the most distant black hole ever detected, capturing it growing in a stage of never-before-seen infancy near the dawn of time. This record-breaking black hole could help solve one of the key cosmic mysteries. Join us today as we dig deep into how James Webb's new discovery could help solve the puzzle of the first black holes. Starting in the late 1950s, we began observing energetic sources in the universe that didn't match any known class of object. As we moved beyond optical astronomy and started exploring the universe in other wavelengths, new types of objects began to emerge. With the advent of radio astronomy, certain sources appeared to emit large amounts of radiation with either no visible light counterpart or simply a single unresolvable point of light. These quickly became known as either quasi-stellar radio sources or quasi-stellar objects, which were both eventually revealed to be the same class of objects, quasars. When we began looking at these objects in X-ray wavelengths of light, we found that they weren't just bright and energetic at those wavelengths as well, but that they were often varied rapidly at X-ray wavelengths. With improved telescopes, optical counterparts began to be identified. These objects turned out to be galaxies, although often faint and ultra-distant. Then, in 1971, the first anomalous X-ray source within our galaxy, Cygnus X1, was identified. We soon came to understand that we were looking at two examples of the same type of object, a black hole. Moreover, these weren't isolated black holes but black holes that were actively feeding on some sort of matter, accelerating it, and causing the emission of radiation of a wide variety of frequencies and wavelengths. We now know that black holes exist with all sorts of properties like masses and rotation rates and in many different locations, including within our own galaxy as part of multi-star systems, at the centers of most galaxies, and even flying through the intergalactic medium. The ones at the centers of galaxies are particularly interesting because they're not of comparable masses to heavy stars, but rather rise up into mass ranges spanning millions, billions, or even tens of billions of solar masses. At the center of the Milky Way, a 4 million solar mass behemoth lurks, and we've even reached the technological point where we can observe individual stars near the galactic center orbiting a point that emits no elliptical light at all. We can be extra certain that these objects are indeed black holes, because we've directly imaged their event horizons in radio wavelengths of light. The black hole at the center of the nearby active galaxy, Messier 87, was the first one ever imaged, which is more massive than the one at the heart of the Milky Way at 6.5 billion solar masses. However, we've observed the Milky Way's central black hole directly as well, showing us that the objects that look like black holes and act like black holes really are black holes, with properties consistent with everything we think black holes should and shouldn't be able to do. Alongside these sets of observations, we also have extraordinary X-ray data that comes to us from numerous space telescopes, including NASA's Chandra X-ray Observatory, a cosmic workhorse celebrating its 24th anniversary this year. Despite being a relatively small observatory in terms of its physical size, Chandra has incredible angular resolution, owing to the extremely small wavelengths of X-ray light it's sensitive to. It has witnessed activity from our own Milky Way's black hole and helped us find stellar mass black holes that would be otherwise invisible to our arrays of observatories on Earth and in space. In particular, it's even taken deep field images of certain regions of the sky that don't have a lot of light-absorbing hydrogen gas in them, revealing enormous numbers of what can only be very distant supermassive black holes, all at the centers of presently active galaxies. In one long exposure region of the sky, Chandra discovered more than 300 supermassive black holes in an area spanning barely a tenth of a square degree of the sky. Meanwhile, in infrared wavelengths of the sky, also excellent for identifying black holes, NASA's Spitzer Space Telescope similarly discovered enormous numbers of supermassive black holes. Now that Spitzer has been superseded by arguably our most ambitious space telescope of all time, the JWST, the hunt for the earliest and most massive black holes has gotten an additional boost. Prior to the JWST era, a large number of quasars and active galaxies had been discovered not just in the late-time, well-evolved universe, but also at very great distances, which correspond to very early times in the young universe. Many black holes that had already grown to several hundred million or even a billion or more solar masses, black holes that are hundreds of times the mass of the Milky Way's central and most massive black hole, have been found from time periods that correspond to the universe being less than a billion years of age since the hot Big Bang. These early, but still very massive black holes have posed an interesting puzzle for astronomers. If the only black holes that we can form come from stars, and stars top out at a few hundred solar masses, then how did these supermassive black holes, in such a short period of time, grow from such small seeds to be so massive so quickly? This is where we have hoped the James Webb Space Telescope would come in and help us resolve the puzzle. After all, it's pretty clear that if you require stars to make black holes, and black holes that you make from stars top out at a couple of hundred solar masses, and black holes have a maximum rate, the Eddington rate, at which they can grow by accreting matter, then our standard calculations for how black holes should get based on known physics fail to give us predictions that align with what we've already observed. Something somewhere must be wrong about our assumptions, models, or calculations. Numerous possibilities abound. It could be that the universe was born with black holes before any stars formed at all, a population of primordial black holes, if you will. However, there are many theoretical and observational reasons to disfavor this scenario. Primordial black holes would necessitate new physics. It could be that the first stars were more massive than current stars, as they were less efficient at cooling and collapsing, meaning that they require more initial mass to collapse from. However, models indicate that even with initial seed black hole masses of greater than 1,000 solar masses or so, which might be reasonable estimates for the first stars, these black holes simply grow too big too fast for this alone to solve the puzzle. One fascinating possibility put forth only in 2022 suggested that overdense clumps of matter, clumps that might be as massive as several tens of thousands of solar masses, might directly collapse to form black holes, just as some stars seem to wink out of existence with no cataclysm, presumably forming black holes spontaneously. These strong, cold accretion flows of matter can trigger the rapid collapse of dense clouds of matter, perhaps creating seed black holes up to the 30,000 to 40,000 solar mass range. Massive enough that if these seeds were formed when the universe was just 100 to 200 million years old, we could finally put this puzzle to rest. And that's where James Webb comes in. Whenever you look at the universe with new, superior tools, the only thing you should be certain of is that you'll find something, and maybe multiple things, that surprise you. And so it was in July of 2023 when researchers from the JWST collaboration reported the discovery of CEERS 1019, a black hole of 9 million solar masses coming from when the universe was just 570 million years old, breaking the record for the most distant black hole. So long as this black hole represented no more than less than 1% of the total mass of the galaxy, which it did, the universe should have no problem forming black holes this massive this early. However, if we were to discover what's known as an overmassive or outsized black hole, where the supermassive black hole is actually comparable to the total mass of the galaxy, then that would present a challenge. After all, how could a black hole, which requires a continuous source of mass to grow at the maximum rate possible, grow to be so massive that it's comparable to the mass of the galaxy that houses it? Yet, that's precisely what makes this latest discovery, a new record breaker for the most distant black hole known as a Z1, so compelling. When JWST looked at Pandora's cluster, also known as Able 2744, it discovered a great many galaxies involved in a cosmic smash-up, as well as many gravitationally lensed background galaxies whose light was distorted and magnified by the cumulative mass of the foreground galaxy cluster. With an X-ray overlay to top it, one object simply jumped out at astronomers, known as a Z1. It comes to us from when the universe was just 470 million years old, or 3% of its age, contains a black hole that's somewhere between 10 million and 100 million solar masses from the brightness of the X-rays as seen by Chandra. But where the total stellar mass of the galaxy, from JWST observations, is also only between 10 to 100 million solar masses. This one discovery, in concert with everything else we've learned to date, teaches us a gigantic lesson. For one, it tells us that the small seed scenario, where supermassive black holes grow from stellar mass seeds, cannot account for a Z1. There's an upper limit to how quickly black holes can grow, and that's in part determined by their environment. With so little mass available within its host galaxy, a Z1 couldn't have reached 10 to 100 million solar masses in just a few hundred million years if it began from such a small seed. And, as Andy Golding, lead author of the study that reports the galaxy's distance and mass put it, there are physical limits on how quickly black holes can grow once they formed, but ones that are born more massive have a head start. It's like planting a sapling, which takes less time to grow into a full-size tree than if you started with only a seed. But a large black hole seed, between 10,000 and 100,000 solar masses, could have formed from directly collapsing gas and then grown by consuming the matter that falls into it. As matter falls onto the black hole, it will form stars and also grow the black hole, with theoretical predictions indicating that over a few 100 million years, the black hole seed will start off outmassing the stars around it. Then, both the mass of the black hole and the mass of the surrounding stars will rise, but with the mass and stars rising more quickly, causing the stellar mass to eventually catch up to and then surpass the mass of the more slowly growing central black hole. Up until a Z1, we had never found a black hole more massive or as massive as the cumulative amount of stars that surrounded it. But we'd also never found a black hole as early in the cosmic history as a Z1 either. This is a central piece of evidence in revealing our cosmic history. If we put all the pieces together, we arrive at a scenario where, sure, the first stars will definitely give rise to large numbers of black holes, up to the hundreds or perhaps even 1,000 solar masses each. But the seeds of supermassive black holes were more likely formed from the direct collapse of gas, leading to black holes of tens of thousands or maybe even 100,000 solar masses appearing just as the very first stars are only igniting. Then, as gas accretes and collapses, those black holes grow, but the stellar mass in galaxies rises more quickly, with stars catching up to the black hole in mass after a few 100 million years and then surpassing it just a few 100 million years later. It doesn't require us to assume any novel or exotic physics like primordial black holes, but rather to accept that black holes can indeed form from the direct collapse of matter, creating large seed black holes of at least 10 to thousands of solar masses independent of any stars that form, live, die, and create black holes themselves. This observation also teaches us that the James Webb, Chandra, and the power of gravitational lensing enhance all types of light from distant background objects. But we fully expect that large numbers of these early black holes, even ones in young galaxies with relatively small numbers of stars, will eventually be found, allowing us to test the details of this emerging picture of how galaxies and black holes are connected. Perhaps this long-standing cosmic question of how black holes got so massive so quickly is finally nearing a satisfying resolution. What's interesting, not only focused on the first black holes, is another remarkable discovery. James Webb just detected clues about how Earth formed billions of years ago, specifically the telescope's planet-forming disks letting off a cold steam, providing crucial evidence for a leading theory describing how planets are built. This excess water vapor was detected by the James Webb Space Telescope in two compact disks of gas and dust surrounding young stars that are just 2 million to 3 million years old, which is incredibly young in the scope of our universe's timeline. The disks are located in the Taurus star-forming region, which sits about 430 light-years away. Astronomers believe planets form through a process that begins with what is termed pebble accretion. This involves small chunks of silicate rock ranging in size from centimeters to about a meter that are coated in ice. They're thought to begin their lives in the freezing outer parts of a planet-forming disk, typically home to comets, and eventually start to experience